Alright, welcome. In this video, I'm going to be giving you reason to believe me when I tell you that the derivative of e to the x is e to the x. Now, this is something that, of course, is true, and it's true for a variety of reasons, and therefore there's a variety of ways I could show you that this is true. A lot of it is going to come back to what is your definition of e, though. And that's something that I would just will barely mention in my AP Calculus class. I definitely won't go into this, just because I don't have time for it. But I will remind you that at least in my class, our definition of e is, we take the limit definition. So it's the limit of, I'll just write it out. It's the limit of 1 plus 1 over p to the p power as p goes to infinity. Now, that's great. That's, usually what most people would think of when they think of definition of e. But I'm going to want to take a different definition today. It's equivalent to this one. I'm really going to make the substitution. I'm going to just say let n equal 1 over p. It will be the case that as p goes to infinity, n goes to 0. So this is the same as, I didn't say that was equal to e, but so I'm going to say that this is the same as the limit as n goes towards 0 of 1 plus n to the 1 over n power. Because if n is equal to 1 over p, then p will equal 1 over n. Okay. So I'm going to need that. I'm going to come back on that right at the very end. Okay. So in order to prove this, I'm going to start with the definition of the derivative. Okay, right? I'm going to say that the derivative with respect to x of e to the x is going to be the limit as h goes to 0 of e to the x plus h minus e to the x divided by h. It's the limit of rise over run as run goes towards 0. Now what I'm going to do is I'm going to, just rewrite that. I'm going to basically use an exponent property. There's going to be lots of exponent and log properties going on here. But I think that would be expected working with an exponential function. So that's going to be the limit as h approaches 0. And I'm going to write this as e to the x, e to the h. Maybe I'll write it as e to the h, e to the x. Right? And then you'll probably see what I'm supposed to do here. Definitely want to factor out an e to the x out of both of those. And yeah, start over here, because I think I'm going to start to need more room. So the limit as h approaches 0 of, I'm going to factor out an e to the x, and I'm left with e to the h minus 1 divided by h. Now, this e to the x thing right here, it doesn't care what happens to h, right? It only depends on x. And for that reason, I'm going to factor it out of the limit. And so I'll really only be concerning myself with this limit right now. So I will go over here and I'll write equals e to the x multiplied by the limit as h goes to 0 of e to the h minus 1 over h. All right? And now what I'm going to do is I'm going to start working on this thing. Okay? So I'm going to say, I've got this idea. Let n be the numerator of this fraction. Okay? So I'm going to say, let n equal e to the h minus 1. Okay? That would mean that n plus 1 equals e to the h. And if I'm going to substitute on this and get rid of all the h's, then I probably want to get rid of that h as well. So I'm just going to solve for h right here and say h is the log of n plus 1. I guess I should probably, in this video I'm mentioning my definition of e, I would define natural log to be the inverse function for this. Okay? I think that that's an appropriate definition. Okay, there are definitely other ways you can go. You can say that the definition of e to the x is the solution to the differential equation y prime minus y with the initial condition y of 0 is 1. You can define natural log in terms of the area under the graph of a different function, which, you know, where you are in the class, you might not be understanding what that really is all about yet. And that's fine too. But up to this definition and then the consequential definition of natural log, this is what we're going to have. All right, so transforming this into n's, I now have, so I have an e to the x, and I'll be taking the limit. And now let's think about this. As h approaches 0, what's happening to n? As h approaches 0, I have e to the 0, that's 1, minus 1, n is going to 0. So n is going towards 0, and I'm going to have, okay, e to the h minus 1, I define that to be n. And then in the denominator, I'll have h, which was the natural log of n plus 1. And now what I'm going to do is I'm going to take this this fraction on the inside of the limit, and I'm going to multiply it by a clever form of 1. Multiply it by 1 over n divided by 1 over n. All right, in the numerator, I'm going to have 1. But then in the denominator, I'm going to have 1 over n times the natural log of n plus 1. Okay? And, well, that's the type of thing where I'm just going to remind you of a log property. I think I'm going to actually write this down in blue, and then you can see what I'm talking about. So if I've got something multiplied on the outside, like m times the natural log of some argument, what I can do is I can take that and make it an exponent. Okay, so this is the natural log of a to the m. Okay. So I'm going to write this now as e to the x times the limit as n goes towards 0, yeah, one more time, of, in the numerator I have 1 over natural log of n plus 1 to the 1 over n power. And now you should start to see where I'm headed. The log of, what is it? Maybe I'll call this 1 plus n to the 1 over n power. Fraction, yeah. All right. And then, let's see, how did I write this? Yeah, all right. So the thing about natural log is that for a place where it's defined, it's a continuous function. And one of the things about continuous functions that we didn't really need to do in my AP Calculus class, because we don't actually, get in there and work a lot with the nuts and bolts of limits, but is if you're working with a continuous function, I can pass this limit through to the inside. So this limit is equal to 1 over the natural log of the limit of this. And so I'll have, I'm just going to rewrite it. So I've passed the limit through the inside as the log of the limit as n goes to 0 of this. Okay. Ask you to recognize that in the denominator here, this limit that I'm underlining in green, that's e, right? The limit as n goes to 0 of 1 plus n to the 1 over n power. Hold on, I copied that wrong. Right? This should be all right. So now I'm multiplying e to the x times 1 over the natural log of e. The natural log of e, what exponent do I have to put on e to get e? That would be the 1 exponent, so I've got 1 over 1, that's 1 times e to the x, and that is e to the x. So this is why, up to our definition of e, why the derivative of e to the x with respect to x is e to the x. And in a later video, I'll probably show you about the derivatives of 2 to the x, 3 to the x, 10 to the x, really exponentials that don't have bases.